Hello everyone, my name is Myriam Legault. I'm here to speak about the master's thesis that I did last year to study the efficiency of early bellows and tuyeres. My methodology was experimental archaeology, so I'm delighted to present my paper at the EXARC conference. I believe my research was innovative on several aspects, mainly the topic and the measuring instrument. So far, the efficiency of bellows and tuyeres for forced draft was specifically discussed in only 4 sources that I could find. The bulk of the research focused rather on other airflow methods, natural draft furnaces, wind-powered furnaces, and blowpipes. The oldest bellows were found in the Levant and Egypt in Bronze Age layers. Only the baked clay pots of the Bronze Age bellows were excavated by archaeologists. The leather diaphragms had long since decayed, which means that we cannot know if these early pot bellows had a valve or not. Bowl bellows, with and without valve, were still commonly used for iron smelting across sub-Saharan Africa until the 20th century. Accordingly, even though early types of bellows were the subject of my research, I relied heavily on African ethno-archaeological literature to design my experiments. Roman and Greek sources evidence that another type of bellows was also prevalent during the antiquity, the back bellows. Given that ancient back bellows were entirely built from organic materials, no archaeological examples have yet been found. However, this simple bellows was used throughout many regions of Eurasia and Africa, and this even up until the 20th century in sub-Saharan Africa. Organic bellows are normally used for metallurgy in conjunction with inorganic tuyeres, so as to avoid setting the bellows on fire. In this project, I studied the most common types of tuyere, the cylindrical and funnel-shaped tuyeres for single bellows, and the forked tuyere for double bellows. The cylindrical and funnel-shaped tuyeres represent the oldest known types of tuyeres, while forked tuyeres are recorded from a few Iron Age sites in Western and Central Europe, as well as from Greek and Roman sources. Here's a summary of my experiments. I investigated 3 types of bellows and 2 types of tuyere. Afterwards, I had to choose how the bellows were to be operated. For pot bellows, the obvious choice was to blow them with the hands rather than with the feet, like in Tuyère's tomb from the previous slide. Next, the choice to operate a bellows with 1 or 2 hands was fairly important, given that pumping with 2 hands doubles the applied force. Following the archaeological literature, I chose to analyze foremost the double bellows setup, and then secondly the single bellows setup with 2 hands to blow the lone bellows. This is a drawing of one of my 2 identical pot bellows. This particular valve design is neither evidence in African ethnoarchaeology nor, of course, on any archaeological specimen. However, the valve is inspired by the foot bellows depicted in Tuyère's tomb, only a strap attached to the leather cover was added and a long pole, here, replaces the rope for pulling. I believe that my valves, and by extension my pot bellows, work better than most other African pot bellows types in terms of ease of use, reduction of air leaks, and achievable pumping speed. My valveless pot bellows, drawn here, simply replicates the basic design from ethno-archaeological accounts on African iron smelting. My back bellows, pictured on this slide, are also fairly standard. They reproduce the bellows I encountered on metallurgical experiments in Germany, and their design doesn't diverge significantly from the back bellows described in the African ethno-archaeology. The pot's dimensions for my pot bellows fall a bit over the average dimensions for archaeological and ethno-archaeological bowl bellows. Why did I make them slightly oversized? Because the bellows are not completely emptied on each downstroke, and when the bellows are pumped slowly, the volume of air left inside after each deeper downstroke is even smaller. Consequently, I built my bellows on dimensions with which I felt comfortable for pumping, and with a few centimeters added all around to ensure that the bellows remain only half emptied with slower pumping. The dimensions, that is, the length and the bore diameter, of my tuyeres also fall around the averages for archaeological and ethno-archaeological tuyeres. The inner angle of my standard fork tuyere is 40 degrees, roughly the angle of the Hjortspring box tuyere and close to the angles of other archaeological fork tuyeres. I chose to build both my bellows and tuyeres out of modern materials because the use of fake leather for the bellows and of plastic for the pots and tuyeres doesn't make any mechanical difference. On the flip side, however, modern materials like PVC pipes connected by appropriate couplings are completely airtight. Considering that I'm investigating the airflow, minimizing air leaks to avoid bias was my primary concern. I could have eliminated air leaks by sealing clay tuyeres together with wet clay, but my measuring instruments were to be fitted inside the tuyeres and don't work well outdoors, with sudden gusts of wind. What kind of measuring instrument did I use? A pitot tube, an instrument to measure the flow velocity of a moving fluid. Its main sensor directly faces the airstream to measure its total pressure, while a second sensor placed perpendicularly to the airstream measures the static pressure. The difference between these two pressures, the dynamic pressure, is a function of the flow velocity, which can then be calculated. Pitot tubes afford several advantages over the more commonly used anemometers that measure the average airspeed of bellows. First, they can be mounted inside the tuyeres and will therefore measure the bellows airflow without interferences from outside air currents. Second, they record the airflow speed about 50 times per second, which approximates its instantaneous velocity. And third, it is possible with two or more pitot tubes inside tuyeres to record the airflow at different locations and orientations in the tuyere system. For example, to measure simultaneously the air flowing back and forth from valveless bellows, or to detect the airflow diverted by a forked tuyere. The pumping movement, and thus by extension the airflow speed, represents a periodic oscillation illustrated as a sinusoid. When blowing a single bellows, there is no airflow at least 50% of the time. Even for double bellows blown in perfectly dephased sinusoids, the airspeed will still drop to zero between each stroke. The only way to ensure that some air continually flows out of the tuyere is to operate 3 or 4 bellows together towards the same tuyere. I considered that 3 variables were relevant to quantify the performance of bellows and tuyeres, at least solely as regards the airflow. The most important variable is the volumetric flow rate. On my speed time graphs, the volumetric flow rate corresponds to the distance traveled, that is, the area under the curve multiplied by the area of the tuyere's bore. The maximal airspeed is second in importance to the flow rate because it determines how far the airstream can penetrate the furnace bed, how big the size of the reaction zone. And the least essential of my 3 variables, the percentage of time without airflow, was measured to quantify the airflow's regularity, especially with respect to single versus double bellows. The bellows were operated by volunteers rather than by a motorized device, which means that some degree of human variation was introduced in the experiments. In accordance with the ethno-archaeological literature from Africa, those 3 volunteers on the bellow were a woman, an older man, and a younger man. They pump the bellows at a stroke rate of 30 circles per minute, a stroke rate common in experimental archaeology. This first experiment collected preliminary data for comparisons, but a few observations could be made with the pot bellows. First, my slightly oversized pot remained half full with air when pumping it as a single bellows. Second, the volume of air blown on each stroke of a bellows was further halved by pumping double bellows. Likewise for back bellows, less than half the bag's volume was blown on each stroke, and blowing 2 bellows rather than 1 halved the air volume flowing out. Another observation is that bellows operators often pumped each arm with different levels of strength. A 10 to 20% difference in maximal airspeed between each bellows of a pair was common. From my experiment on the fork Tuyere, data showed that a narrow fork was more efficient than a wide fork, since the volumetric flow rate of the 60-degree fork represented about 3/4 of the one from the 40-degree fork. Nonetheless, the narrow 40-degree fork was still pretty problematic too, because a significant proportion of the airflow from the first bellows was diverted through the fork towards the second bellows of the pair. As a matter of fact, a third of the pump volume was lost through the 40-degree fork, either diverted towards the second bellows or just slowed down inside. Conclusion: the fork Tuyere is not an efficient channel to convey the airflow. It has been speculated in the literature that funnel-shaped tuyeres were used to take advantage of the Bernoulli's effect, which is when an airstream flowing at high speed inside a funnel draws in the surrounding air. In this experiment to test the funnel-shaped tuyere with pot bellows, I varied the distance between the nozzle and the funnel. As you can observe on the chart, the highest volumetric flow rate at the fire end occurred when the bellows nozzle was pushed as far as possible inside the funnel, when the gap between the two became almost non-existent. Consequently, the Bernoulli's effect does not begin to compensate for the massive air leak at the gap between nozzle and funnel. Conclusion on my three tuyeres: the simplest tuyere type, the cylindrical tuyere, is the one which conveys the airflow the most successfully. Valveless bellows represent the only reason to prefer funnel-shaped tuyeres over cylindrical tuyeres sealed with clay in an airtight manner. Given that a valveless bellows both sucks in and blows out the airstream to the nozzle, it requires a gap between nozzle and tuyere to avoid drawing in the hot air and the sparks from inside the furnace. But because of this gap and of the back and forth of the airflow in the nozzle, valveless bellows are more physically demanding to pump and they produce less airflow. I sketch here on the right side the typical airspeed peak of the air flowing into the valveless bellows. These peaks have broken tips because the blowers were just too tired to complete the movement that they usually do on bellows with valve. Moreover, when asked to pump as fast as they could, the blowers only managed to pump the valveless bellows 15% faster than usual. For back bellows, technique and stamina are more important when pumping. First, because a stroke with a back bellows incorporates many different gestures, which have to be carefully coordinated when pumping double bellows, one per hand. Second, because the fastest method of pumping the back bellows relies mainly on moving the hands and the forearms, not the upper arms. So those weaker muscles tire faster with unpracticed bellowers. From these charts, the general conclusion is that pot bellows with valve function better and blow more air than valveless bellows or back bellows, at least for my valve type. However, it should be noted that I have two outliers among only 13 data markers for the left chart and one outlier in 9 data points in the right chart. Because of my insufficient resources and time to conduct this short project for my master's degree, my experiment was affected by a few problems. First, in terms of data quality, the pitot tubes for aeronautics bought on Amazon were made to measure the higher airspeeds from aircrafts, not the low and irregular airspeeds from bellows. My calibration of the two pitot tubes was also a bit crude. I reached a 10% standard error that I deemed good enough for this project. Second, in terms of data quantity, it would have been preferable to test with a bigger sample, by employing more than 3 people and by making them repeat each experiment more than twice. The small sample size was not enough to offset the variation in performance that comes from testing with human bellowers. Given these issues, the specific numbers of liters per minute or meters per second measured should be understood as approximations. Nevertheless, my conclusions are reliable since they were drawn only when the data indicated clear trends or differences between bellows or tuyeres. I hope that the detailed observations presented in this paper convince you of the great potential of pitot tubes for measuring the airflow from bellows. I look forward to other archaeological experiments measured with pitot tubes, or even with anemometers, so as to see more data for comparisons on the performance of bellows and tuyeres. That was my paper. Thank you for listening to me.